Hello everybody, here we are again. Once again, we're now on module 13B, lab 27. If you'll turn there in your little student book, that would be great. Quick question, I sent out the quiz for module 12 and I haven't received any completed quizzes back. So did you not get them? I believe somebody emailed me and said you got it, and I can't remember if I sent it through Google Classroom. I also did set up a Google Classroom, which should have sent you an invitation to become a part of the classroom. About half of you have responded to that. So if you need me to send that back out, email me, let me know that, and we'll see if we can get that worked on. Okay? So we're continuing on now with our study of the forces. Oops. So remember the four fundamental forces. This is fundamental, right? First we had gravity. Then the electromagnetic force. We had several, labs on both of those. We have the strong force, which we talked about last time, which remember is that very strong force that's holding protons together inside the nucleus. And then we have the weak force. This is the one we'll be talking about today. Let's do a little review, however, on our periodic table of the elements. Remember, this is inside the cover of your book, I believe, and or in your module, somewhere in module, the previous module. So, oh look, it says here page 321. There we go. When you take a quiz on this module, you will be able to have your periodic table of the elements with you. We're just going to ask a few questions right here, just to see it, just a little practice with it, okay? So, what is the name of an element that has 40 protons? So you're going to go back and you're going to look at your chart and you're going to look for what? You're going to look for the number 40 as the atomic number, right? And the next thing you're going to look for is what is the name of the element with the letters PB. So look that up on the chart. I'll give you a few minutes to look that up. All right, so number 40 we see is zirconium. ZR is its atomic symbol. You see the 40 right up here in the corner. That means it has 40 protons. Next, PB. You don't get it from the letters that it's the word lead. That's strange, right? Apparently plutonium or something like that is the name of this in Greek or Latin or something. You can see right here how many protons does it have? 82. Okay, very good. Now let's move on to the weak force. The weak force is related to the electromagnetic force, and some people may argue that all these forces are related, maybe except with the exception of the strong force. It governs something known as radioactivity. All right, so that's a concept we're going to be talking about a lot today. What in the world is radioactivity? If we have an isotope that's radioactive, it's an atom, here we're underlining this, an atom with an unstable nucleus. All right, so the nucleus is not stable. It tends to be, it tends to want to fall apart. All right, so it usually has to do with the number of neutrons it has. It may have too many or even too few neutrons. It just makes it where it's not balancing out right. It's like it's off balance. So radioactive decay radioactivity is a form of decay. Decay is to break down. So that's when an atom releases a particle or energy, some sort of energy, to become stable. So it's going to become balanced by either getting rid of something or letting off some light. So we're going to look, there's different types of radioactivity. So types of radioactivity decay. Here we go. Number one, beta decay. Beta decay. All right, when a neutron becomes a proton by releasing an electron. Okay, that is weird. What does that mean? Well, it turns out that in some of these unstable atoms, they have too many neutrons. And the neutron will start to, itself, the actual neutron will fall apart and it will spit out a little part called a beta particle, which is actually a negatively charged little particle. That's what we call an electron, right? And then what's left behind is a positively charged something. Remember, a neutron's just slightly bigger than a proton, so it actually becomes a proton. It's really kind of weird. We'll watch a video in just a minute. Alpha decay, a nucleus also falling apart, releases two protons. Just normal protons get released out of the, they actually get kicked out of the nucleus along with two neutrons. So then we have something that's made up of two protons and two neutrons leaving. So you should know what that is. Something with two protons. What is that? Look at your chart. It's helium. And that's what happens in alpha decay. Gamma decay, gamma radiation is a release of energy typically visible as light. Okay, so it's glowing. Oftentimes, if you see some of these, science fiction movies or something, and somebody's dealing with something radioactive, it's glowing. And that's accurate, okay, especially if it's going through gamma decay. In fact, some of these, even beta and alpha decay, can sometimes also release light, release some energy, because energy is being released when this takes place. So let's start with beta decay. You see right here, so we're looking at just a neutron inside of a atom, right? Inside of a nucleus right here. And what happens is it spits off little pieces here. It spits off a little beta particle, which is actually negatively charged, so that's an electron, and some weird little thing called a neutrino, and it's left behind a proton. All right, so we're going to see what does that do for us. If we have a proton, it looks like we've added a proton, right? And that's going to change our atom. Let's see how this happens. Let's watch this.
Radioactive decay begins with an unstable nucleus. Consider, for example, the unstable nucleus uranium-239. Now, we're only looking at the nucleus here. The electrons are far, far away. Since it's uranium, we know it has 92 protons. Since it's uranium-239, we know that the total sum of protons and neutrons in the nucleus is 239. Therefore, if we know there are 92 protons and 239 total in the nucleus, there must be 147 neutrons. This nucleus is unstable. It has too many neutrons. So it needs to change its configuration so it has fewer neutrons and more protons. Here's how it happens. Through a process that's not very well understood, the neutron somehow finds an electron within itself. It then spits that electron out. Now think about it. Neutrons are neutral. They have no electrical charge. If something that's neutral spits out a negative charge, what happens to it? Well, it was neutral. It got rid of a negative charge. Therefore, it must now become positive. In other words, the neutron turns into a proton by spitting out an electron. So now this is no longer uranium, because it doesn't have 92 protons anymore. It has 93. Atoms with 93 protons are called neptunium atoms. This particular neptunium atom still has 239 things in its nucleus. After all, it didn't spit out a neutron, it spit out an electron, and electrons don't count in terms of the nucleus. Only protons and neutrons do. By simply changing a proton into a neutron, the total number of things in the nucleus didn't change. So this is neptunium-239. Now that electron that was spit out by the neutron, that continues to speed away from the nucleus. It's called a beta particle, and that's actually the source of the danger behind this kind of radioactive decay. That beta particle is moving so quickly that it acts like a little bullet, and that little bullet could either kill one of your cells or mutate your DNA. If enough of that occurs, you can be in serious trouble.
All right. Pretty interesting stuff, huh? And that's why radiation is bad for us, right? Alpha decay, a little different right here. We're going to have the parent nucleus over here. All right, we're going to have the decay event and send off 2 protons, 2 neutrons. That is helium. And we're left with a daughter nucleus. Okay, these words are important here. Parent and daughter. Notice this is called an alpha particle. Yeah, it's helium, all right, but we call it an alpha particle because, once again, it's being kind of shot out of there. And we end up with our daughter nucleus, which is now different because 2 protons are missing. We have another video.
Alpha decay, like all radioactive decay, starts with an unstable nucleus. Consider the unstable nucleus polonium-214. The periodic chart says any polonium atom has 84 protons, so we know this has 84 protons. It has a total of 214 protons and neutrons in its nucleus. Well, if the total is 214 and there are 84 protons, there must be 130 neutrons. This is an unstable nucleus, so it needs to change its configuration. The way this nucleus changes its configuration is by actually taking 2 protons and 2 neutrons and spitting them out of the nucleus. Once these protons and neutrons leave the nucleus no longer has 84 protons because it spit 2 of them out. So it now only has 82 protons. Well, any nucleus that has 82 protons is a lead nucleus. So this is now lead, not polonium. Also, it no longer has 130 neutrons. It spit 2 neutrons out. So it has only 128 neutrons. A nucleus that has 82 protons and 128 neutrons has a total of 210 things in its nucleus, so this is lead 210. Now those two protons and neutrons that got spit out of the nucleus, they stick together as a helium-4 nucleus and speed away from the remaining lead 210 nucleus. We call that an alpha particle, and just like beta particles, alpha particles are traveling so fast that they act like little bullets, which could kill cells or damage DNA. That's the source of danger from alpha radiation.
All right. And then gamma decay is a little different. What happens here is that we have actually the release of energy. So you were going to talk about this toward the end right here, this release of energy right here in a photon. So if you remember, a photon is a particle of light, a wave particle of light. And so this is when we're going to see the glowing taking place right here. So what happens in this particular case is that we have the breakdown of the nucleus. Instead of sending out physical parts, though, it's just sending the energy out. So when the energy comes out, it helps relieve that stress of instability. And so that light ray comes out, releasing some of that pent up energy. So we're going to look here. These are the kind of problems you may have to answer on a quiz. Okay, so what element is left after radioactive decay? So we're going to be looking at example 13.3, and your OYOs 13.7 and 13.8. In the study guide question, pay particular attention to 14 and 15. It says here to put those in a space on your lab sheet. So if that's there, then go ahead and you'll be doing that in your work. That's the study guide, right? So study guide, you're going to be doing it anyway. And so just see if you have a place on your book to put that in. So we're going to be looking here at the first one, example 13.3. It's on page 329. Okay, C14 is a radioactive isotope, that's carbon-14, that goes through what kind of decay? Beta decay. So remember what that is. So we're going to be looking at the daughter product of this decay. So what happens in beta decay? Remember, a beta particle gets removed. So how is that going to change my carbon-14? Think about it. You can pause this video if you want to think about it longer, okay? Carbon has the atomic number 6. You find that on your chart. So carbon-14 has 6 protons and 8 neutrons. During beta decay, 1 neutron becomes a proton. So the daughter product will have 7 protons and 7 neutrons, which becomes a new atom called nitrogen. Nitrogen-14. How about that? Not too bad, huh? Not too difficult. All right. TH232 is a radioactive isotope that goes through alpha decay. What is the daughter product? So remember, alpha decay is a little different. What's going to be gotten rid of during alpha decay? What is shot out? What is the alpha particle? Remember that? Helium, right? Okay. It's thorium. It has 90 protons and 142 neutrons. That's just math. During alpha decay, it spit out 2 protons, 2 neutrons. That's a helium. The result will be 88 protons and 140 neutrons. And if you look that up on your periodic chart, you will see that 88 protons belongs to radium, right? So there you go. Next one, these are probably the easiest ones right here. If a Y90 atom undergoes gamma decay, what nucleus will be produced? Okay, notice it doesn't say daughter product here. It says what nucleus will be produced. A little bit of a trick right here. Gamma decay simply takes the energy out of the nucleus, so the daughter product is still the same thing. All right, so those are the best ones. They're very easy. Okay, practice some of those. We'll have a few of those on your quiz. So we talked about how there is a danger to both of these types. Well, really all 3 of these types of radiation. Gamma radiation, that light coming out, can also come out and do damage. But you need to understand there's radioactivity around us right now. It's all over the place. God has really equipped us to handle a lot of it. There's radioactivity. I remember when I was a kid, if I sat too close to the TV set, my parents would say, watch out, you're going to get radiation. So technically, when we're having electronics around us, it's true. I mean, there's some sort of type of radiation. You know, we look at cosmic radiation. It's natural. It's coming from all around the universe, from the sun and everything else. So it's surrounding us, but we have also taken some of these radioactive elements and used them to make energy that we can use. All right, so we're going to see how sometimes that can go awry. This is a map of Japan. Japan is an island nation with very few natural resources. And because of that, they are very dependent on nuclear energy. So nuclear energy would be to take a radioactive element to get more and more of it by, so typically when the radioactive element's going to be the lowest percentage of that element. For instance, carbon 14, carbon 12 is the most common, right? 98% of the time when you find carbon, 98% of it's carbon. And then, 1% of it is, probably 2%, 1.8% is carbon 13, and only that last little bit is carbon 14. So if I'm trying to get a radioactive element, I'm going to try to purify it down so that I can get rid of all the normal stuff and only have the radioactive part of it. Okay, so you take that radioactive part of it and you can put it, I'll show you a nuclear reactor here in a little bit and show you how it works. But anyway, we can use that energy that's being created, those little beta alpha particles, photons coming off of there, and we can use that to make energy. We basically can use it to boil water. And if I boil water, I've got steam. If I have steam, I'm turning a turbine. If I'm turning a turbine, I get electricity to my house. Simple as that. And in Japan, they depend upon it a lot because they don't have coal, they don't have oil and gas there. So right down here in this place called Fukushima, there was a nuclear power plant there. But the other problem with Japan is they are also prone to earthquakes. And what happens sometimes with earthquakes is something called a tsunami, and that's a giant wave that comes over and washes over things. And that's what happened at Fukushima in Japan just about a decade ago, not that long ago. So we'll look at the details of it in a minute. So what about nuclear power? We're going to be looking at a small part of it right here. Okay, so this is the reactor core. And what I have in here are these rods right here of a radioactive material. Usually, uranium, sometimes polonium, but uranium often is what it is because we find more of it. It's right here in this thing. They lower it down in this tank of water, and then the water water boils, creates steam, drives the turbine, which turns the generator, which brings electricity. Okay? We get rid of the water, and it condenses it because it's hot, right? So condensing just means it's going to turn the steam back into water. And then it will be able to get it out here. So this is at Fukushima. That's in Japan. The seawater is diverted to the reactor in an attempt to avert a meltdown. So we don't want a meltdown to take place. What happens in a meltdown? So a meltdown is a major malfunction, okay? What happens is if I should run out of water in my tank for some reason, what if it all boils away? What if there is a faulty switch that tells me I have a lot of water in my tank when I really don't? That's what happened in America. What will happen is that heat will continue. Okay, so those rods have natural heat coming off of them because they're decaying radioactively. And if they continue to keep going, they run out of water, they will literally burn through the bottom of the containment vessel here, down into the ground, and we have what's known as the China syndrome. And that means to dig a hole all the way through the earth, right? It doesn't really do that, but it can break through there. When it breaks through there, this little yellow and black circle right here is showing you the sign for radioactivity. So this stuff, which is radioactive, gets down into the earth and causes a lot of trouble right there. So it has to do with keeping the right amount of water. Here they're trying to keep seawater going in to make sure that it's cool at all times. It's trying to overcome that problem of running out of water by having a fail-safe. The fail-safe is that seawater will always come rushing in. If there's no water there, seawater will rush in just by virtue of where it is, right? So this happened in Russia. This is a place called Chernobyl. This was the USSR, so United Soviet Socialist Republic, before some of these countries got their independence. So it's an independent country now. What is that? That is, I don't remember the name of the country, but it was in Russia at the time. And what happened was this is the area of the Chernobyl reactor. Chernobyl's the name of the city. And it had a nuclear meltdown. All right, it really, really happened. Do I have pictures of that? Oh, sorry, I didn't warn you about this. Afterwards, when we went through and found things, this little deformed puppy was located It shows what the radiation can do to animals. Probably the mama dog was pregnant at the time, got some radiation in her, and this is what happened. This was a result. Sorry about that. I'm going to go back to Chernobyl for a second. Here we go. All right. So the containment vessel, the problem with this particular event was that the reactor that was built by the Russians was not very well built. Let's go back another picture. Remember I say here the containment vessel, right here, if it burns through, this has happened in Chernobyl right here. Okay, it happened by going down into the ground like this. It caused the entire area of Russia there, that whole region, to become contaminated with radioactivity. The people had to move away. People got sick. Some people were killed in the initial, you can tell it was an explosion right there. And so some people were killed there. And it took years and years before they could come back and find some of those remnants of what took place, some of that damage that took place. But the problem is that the Russians built such a lousy reactor that the containment vessel was not strong enough to contain the nuclear material. The idea of a containment vessel is that it has to be strong enough to hold it even in the event of a meltdown of too little water. The Japanese, they did build a very hardy, a very good containment vessel. But we're going to see they had a different problem over there. It wasn't a meltdown in Japan. It was something else. So let's get that one quickly. This is America. This is called 3 Mile Island. It's in Pennsylvania. It's on a little island right there. And they were generating a lot of electricity through this nuclear power plant up there. Now you may wonder, why in the world do we use nuclear power if it's so dangerous? Well, my answer to you is it's not dangerous. In fact, it's one of the most efficient types of electricity we can have. I remember several years ago, one of my sons was in English 5, and one of his classmates was doing his paper. So English 5 is when you present a thesis, and it's a big deal, right? You have this big speech at the end and everything. And this one student was doing his thesis on how terrible nuclear power is because of the radioactivity and this kind of thing. There is some waste. That water has radioactive elements to it, and you have to get rid of it somewhere, this kind of thing. As he did his research, he actually changed his thesis. He changed it to nuclear power is the best way to get power, because it turns out it is incredibly efficient. It really is very, very good as long as you build your reactors safely enough. So as long as it's made correctly, then you can have really great energy creation through nuclear power. So here at 3 Mile Island, there was a near meltdown as well. In fact, there was a movie that was made about nuclear problems. It was called The China Syndrome, and it was made, it's kind of funny, it was made like the year before this actually happened. They were predicting it. There was not a meltdown at 3 Mile Island, but there was a major accident. And what happened was there was a faulty signal that told the people who were running the reactor that there was plenty of water in the core, in the containment vessel, and there wasn't. So it was faulty, right? So the water was running out, and the temperature was going up, but they didn't know the water was running out, and they couldn't figure out why the temperature was going up. And so when they finally figured it out, the accident had taken place where it damaged the core, and it damaged the containment vessel, but it did not dig through the earth. It did not melt down. They stopped it before that happened. Furthermore, our containment vessels are so well built that it wasn't going to go through the containment vessel. All right, but it did ruin the reactor at that particular spot. It continued to work as a reactor for several years after that, but I believe today it has been closed down, mostly because there are other sources nearby. If you look at the map of the world, who has nuclear power, the USA is number one. We have lots and lots of nuclear power. I believe there's even a nuclear power plant down in South Texas, if I'm not mistaken. Here we are. So that big tower you saw over there is called the cooling tower. You saw all that steam coming out of there. So notice it's a lot of big stuff right here. But this is the containment vessel, this whole thing right here. Here's the core. So we need to make sure that this core stays cool, right? So the water is inside the core. Ideally, you know, see, here's our tank right here with our water to make sure it's being filled, our water coming in, all this kind of stuff. Here's our steam generator, right? This is heating up, steam. That's going to go turn my turbine, turn my generator, take it out for electricity. So if at 3 Mile Island, when the water started to run out of this vessel, then it got very hot, and it started to cause damage inside here. But look at this containment tank right here. See, it's very, very thick concrete, reinforced, and all that kind of stuff. So this never was going to dig down all the way through here. It couldn't do it because we built it so well. But they stopped it before that. They found the mistake, and then they turned it off. Essentially, is what they did. They had to go through all this, computer work to get the thing turned off. So the idea is always to keep it cool enough. All right, so we have this decay going on all around us. Like I said, it's natural, right? So in the ground, you'll find some uranium. Part of it's radioactive. It'll be falling apart. It'll be going through decay underground naturally. So how do we measure that? We're going to look at measuring that. We look at something called the half-life. That's the time it takes for half of the original sample of the radioactive isotope to decay away. And that usually takes some time. So typically we're in the classroom, what I like to do is I would stand where, I stand by my computer there, and I'll walk halfway towards the door, and then I'll walk halfway again towards the door, and halfway, and halfway, and halfway. Do I ever actually get to the door? Not quite, because I still have half to get there. I'm only going half. So my first half movement was pretty big, and my next half movement wasn't as big, and then it gets really, 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 really small like that. So we're going to be looking at the half-life of how long does it for half of it to decay. Do you get it? So how long does it take half of it to decay? All right, we're looking at carbon-14. Remember, it is unstable. It goes through beta decay. We end up with a daughter product called nitrogen-14 and an electron and a neutrino. Don't worry about that anti-neutrino thing over there. We use oftentimes carbon-14 to date artifacts. If we find something that used to be alive, it would be made of carbon. The carbon would be in it. And we would look to see how much of the carbon-14 is still there. And so I know the half-life of carbon-14, and I can then make estimates about how old the specimen might be. So if carbon-14 decays into nitrogen, let's see, we're going to see, that doesn't tell me here what the half-life is. No, it doesn't. It doesn't tell me the half-life right here. It's going to be the next slide right there. So this is essentially showing the same kind of picture from the previous slide. I'm going to go from radioactive carbon-14 down to nitrogen-14, and with my beta particle released, which is going to, of course, shoot off like a bullet. Here's our half-life. Oh, this is in general. I start off with pure element. I lose half of it, and I have so daughter product, half, and parent product right there. And then half again, so that's 2 half-lives. Then I'll take out half of these, and then I'll take out half more. You see what I'm saying? Okay, we must have it here. A radioactive isotope with a half-life of 2 hours is used for research. If a scientist starts with 1,000 grams of an isotope, how many grams will be left after 8 hours? Okay, so we're going to be looking at halves now. So in the first 2 hours, how much will I lose? Half of 1,000. So the first 2 hours, I will have only 500 grams of the radioactive isotope left. Do you get it? So now I'm going to lose half again in the next 2 hours. So 4 hours, I'm going to only have 250 grams. You see? So 2 more hours, 6 hours, I only have 125 grams. And we're looking for 8 hours. I only have, that's half of 125 is 62.5. And you see, I could keep going and getting half and half and half and half till I got really, really small numbers, okay? Do you see that? So it's not difficult, especially when you have an easy number like 1,000, right? But a calculator might be helpful in some cases. Okay, here we go. Here's our carbon-14. The half-life of carbon-14 is 5,730 years. Wow. So if something dies and is buried, so here's a tree that's been buried by, let's say, a volcanic eruption or something. After 5,730 years, it's only 50% of the carbon-14 is left. After 11,460 years, only 25% is left. And 12, do you get it? That's half, 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 and half, right? So the idea here is I can take a sample of something that used to be alive, and I can see how much carbon-14 is still there, and I can therefore arrive at some sort of age of that. How long ago did it die? All right, there's lots of assumptions being made here. One, that it was always this number, right? That could have slowed down over the years. Don't know. Another assumption is that when it got covered, all 100% of it was there. But anyway, my point is that it is a good dating system. It tends to fall apart a little bit after only about 3,000 to 5,000 years. So it's hard to date things in the millions and billions of years. Scientists do it all the time. They try to do that. So, but that's the way they do it. Let's watch a little video about this carbon-14 dating.
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we'd count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of two different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
All right. We have another video right here.
Nearly every textbook and science magazine teaches that the Earth is billions of years old, and the primary dating method used for determining this is what is called radioisotope dating, or radiometric dating. Now, this is a reliable method for measuring absolute ages of rocks and the age of the Earth, right? First off, many scientists now regard the age of the Earth to be between 4.55 and 4.6 billion years old. Okay, so if this method is reliable and accurate, why the 50 million year discrepancy? That seems like a lot. But let's get into some details here and see what's going on. Keep in mind that there's all kinds of scientific jargon on this topic, and so we'll just present a very straightforward, simplified version of the process. Radiometric dating is the process of estimating the ages of rocks based on the decay of radioactive elements in them. Basically, there are certain kinds of atoms in nature that are unstable and spontaneously decay into other kinds of atoms. For instance, uranium will radioactively decay through a series of steps until it becomes the stable element called lead. The original element is called the parent element, and the end result is called the daughter element. Radioisotope dating is commonly used to date igneous rocks, rocks which formed when hot molten material cooled and solidified. The dating clock started when the rock cooled. During the molten state, it is assumed that the intense heat forced any gaseous daughter elements to escape. It is assumed that once the rock cooled, no more atoms escaped, and any daughter element now found in the rock is a result of radioactive decay since that rock formed. The decay rate is measured in terms of half-life, that is, the length of time it takes half of the remaining atoms of a radioactive parent element to decay. Now, of course, that can be measured in a laboratory, and it is assumed that since we know the decay rate, we can calculate backwards and come up with the age of the rock. But is that all there is to it? Here's where it gets tricky. It's true we can measure a decay rate using observational science, but there's another kind of science that is required to accurately calculate dates for rocks, and that is what we call historical science. Historical science deals with the things in the past, and therefore it cannot be repeated and tested. Dating methods require both types of science, because in order to get accurate rock dates, one would have to accurately know both the decay rate and the initial conditions of the rock sample, right? Since radioisotope dating uses both types of science, we can't directly measure the ages of rocks. There are assumptions involved. For instance, how do we know what the initial conditions were in the rock sample? How do we know the amounts of parent or daughter elements now in that sample haven't been altered by other processes in the past? How does someone know the decay rate has remained constant since the rock formed? The answer is they don't. Let's simplify here and talk about a typical hourglass. Let's say you walk into a room and you see an hourglass with sand at the top and sand at the bottom, and some sand sprinkling from the top chamber to the bottom. Well, observational science would allow us to see and measure the sand, and then calculate how long the hourglass has been running, right? We could make our sand measurements and then calculate when the hourglass was turned over, right? Well, those calculations could be wrong, because we may have failed to consider some major assumptions, like, was there any sand at the bottom when the hourglass was turned over? Has any sand been added or taken out of the hourglass? Has the sand always been falling at a constant rate? Since we did not observe the initial conditions when the hourglass started, and we haven't been watching the sand all the time since then, we must make assumptions. All three of those assumptions can affect our time calculations. Now, of course, there's more to understanding all of this, but enough said.
Okay, I just put that in there to show you that sometimes, science tends to make assumptions and think because they're scientific that they are okay, right? So that they're sound assumptions. And this was just a little video to show you that scientists make assumptions too, okay? So we have to remember that, and we don't know everything. Okay, when we look at radioactivity, we find a couple of people in history who have kind of blazed a trail to show us how this radioactivity works. In other words, somebody had to figure out about beta decay and alpha decay and gamma decay, right? They had to show us that by going through experimentally to show what was happening, to illustrate what was happening. And so this woman right here was one of the on the forefront of working with radioactive materials. Her name is Marie Curie, or also known as Madame Curie. Let's see her quote. "Life is not easy for any of us, but what of that? We must have perseverance and above all confidence in ourselves. We must believe that we are gifted for something and that this thing must be attained." She was a very hard worker, and she did isolate a brand new element with her husband Pierre. So Pierre and Marie Curie worked in France. She was actually, I think, Polish. She had come to France to be educated, and she stayed there. All right, so what we're going to do is we're going to actually watch some clips from the movie Madame Curie. Okay, because we can't really do radioactive, experiments. We'll do a little lab here at the end. We will just look at this. So you're basically going to watch a little bit of a movie here. It was made in the 1940s. Greer Garson is playing the part of Madame Curie, and Pierre, her husband, is Walter Pidgeon. So just sit back and enjoy. I have a couple of clips. That's her husband.
Well? It's all right. There's nothing wrong with it. I was wrong. I was sure we'd found it. Well, no, I don't know. I'm sorry. You tested all of the elements. You're sure of that, Marie?
Yes, I'm positive, Pierre.
And you found that only two of them, uranium and thorium, gave off rays.
That's right.
Then you measured the uranium and thorium in the pitch blende ore.
And that's when I ran into trouble. The pitch blende had more radioactivity than I could explain by the amount of uranium and thorium it had in it.
Would you like to show me how you make your measurements, Marie?
You wouldn't mind?
Of course not.
All right. Now, here's what I've done so many times that I've lost count. Here is crude pitch blende. Now, we know that the rays come from the uranium and the thorium that are in this pitch blende. Those two elements give off the rays.
Correct.
I put the pitch blende in this mortar.
Has the mortar always been clean?
Always, and grind it up. Here is the ground pitch blende, still with the uranium and thorium in it. I always fill the dish level full. It's just the way I've done it every time. Now I place it in the electrometer. Now I close the case so there's no draft.
Good.
Now I charge the electrometer. Now we'll find out how much energy the rays in the pitch blende have. Is that right?
Right. Start.
Ready?
Read.
Eight.
8.
Same reading I've always had. This pitch blende with the uranium and the thorium still in it comes to 8. Now, here is pure uranium abstracted from the same amount of pitch blende. But This in exactly the same place. Close the case, charge the electrometer. Now we'll find out how much energy the rays in the uranium have.
Right.
Ready?
Read.
Two. Same as always. Done nothing wrong so far.
Not that I can see.
We know then that the pitchblende with the uranium and the thorium in it comes to 8, and that the uranium alone reads 2. Now we test the thorium.
From the same amount of pitchblende.
Of course, put that in exactly the same place. Close the case, charge the electrometer. Now we'll find out how much energy the rays in the thorium have.
Right.
Ready?
Read.
Two.
I don't understand. There must be a mistake. When the uranium and thorium are in the pitchblende, the reading is 8. But individually, they only total 4. Have you checked all the other elements in the pitchblende?
I've checked every element there is. You know the results. Every element in existence. Uranium and thorium are the only elements that give off rays. Why, therefore, do they give off twice as much when they're in the pitchblende as they do when they're tested separately? Where are those 4 missing points? That's what I don't understand. I don't understand.
You made a chemical analysis of what is contained in pitchblende, didn't you?
Of course.
Could I see it?
Yes. Uranium oxide 75%, thorium oxide 13%, lead sulfide 3%, silicon dioxide 2%, calcium oxide 3%, barium oxide 2%, iron oxide 1%, magnesium oxide 99/100%, other extraneous matter 1,000th of 1%.
Yes?
Our universe is composed of definitely known substances, isn't it? Elements that are fixed forever, inert, unchanging. We know that, don't we? All of our science is based on that.
All of our science is based on that. Go on.
In the beginning, man used to think that there were only 4 elements: earth, air, fire, and water. They thought that everything in their universe could be made out of those.
Yes, go on.
But they were wrong, weren't they?
They were wrong.
Now we know that there are 78 elements. Those elements over there on the shelves. And we believe that there are some elements still unknown. But we assume that these missing elements will have the same character as those we know already.
That's right.
Pierre, what if there is a kind of matter in the world we never even dreamed of? What would that mean?
Marie, that would mean that our whole conception of the nature of matter would have to be changed.
It's cold in here.
Tell me what you are thinking.
I don't quite dare.
Go on and say it, no matter how crazy it sounds.
What if we did not make a mistake in our measurements? What if the conception of science is wrong? What if there exists a matter that is not inert, but alive, dynamic? Dare think that our 4 missing points, this strange power, is in that 1,000th of 1%. We have discovered a new element. An active element.
Or a radioactive element, which they were already using. So they kind of use a little high drama right here. But it is true. They've decided they found a new element, and they've got to go through lots and lots of work to get through it. So we're not finished with our movie. Here we go. Next scene of them attempting to isolate this one missing compound.
And so they went on with their work, using every possible precaution. Marie's fingers healed. And though they did not find a way to separate radium from barium in a single process, they did discover a method of removing barium little by little in infinitesimal amounts, working on the theory that once the whole of the barium was removed, nothing could be left but radium.
That's an evaporation dish.
Here we see the sort of thing they had to do. This is called crystallization. When the liquid evaporates, crystals are left. This was the thing they had to do over and over again. It proved to be the most exacting of all the stages of their long task, for it continued for 2 years and required thousands of separate operations. By now, the residue from all the various processes they had worked at lay in hundreds of these small evaporating bowls. Small because larger quantities would not evaporate so quickly. Crystallizing and recrystallizing. Each operation, they hoped, bringing them closer and closer to the heart of the great mystery. At last they arrived at the final crystallization, the one that contained the concentrated result of all the others, the last survivor out of those hundreds of evaporating bowls.
I think I feel like crying.
Ah, Professor Perrault.
Professor Perrault!
Madame Curie, but I'm afraid...
That's just somebody coming to visit to see her work she's doing. But they meet the guy next to him here, and I believe that's Lord Kelvin. So another person who was very much involved in the scientific community at the time. All right, so they're waiting to see if their last evaporation dish will show their element in it. Let's see what happens. She couldn't go, so she sent him to look.
There's nothing there. Not a trace of anything. Not a grain. Only this stain. What's happened, Pierre? Where's our radium? What have we done? Where is it? What's happened? Where is it, Pierre?
I don't know.
What did we do that was wrong? What could we have
We've
done?
done nothing wrong.
I can't stand it, Pierre. Where is our radium? We worked for years and years and years. It must be there. It must be there. 4 long years in this shed. 4 long years.
Is that you?
Yes, Father.
Well, something's got to be done about that child of yours. I think you ought to take it back. I had to stand on my head to make her eat her supper. And now she Now she won't go to bed until her mother tells her a story. I'd like to know what's the matter with my stories. They're the same stories.
I'll go up to her.
Okay, so you see, very disappointed. Although, did you see something in that dish? She's going to figure it out.
Try to put it out of your mind, Marie, and go to sleep.
I can't. I can't accept it, Pierre.
But Marie, sometimes there are things you just must accept.
If I only knew why we'd failed, I think the failure itself I wouldn't mind so much if I only knew the reason for it. Months and months and months ago, we knew we'd found the right process to use. Now, at the very end, why should it suddenly fail?
I don't know. I don't know.
Pierre, that stain on the saucer.
Aha.
Yes?
We didn't even test it, did we?
No, we didn't.
What we were expecting to find was a definite amount of radium, wasn't it? Something we could see and feel. About as much as a pinch of salt, you said.
Yes.
Pierre, what if it's merely a question of amount? What if there's so little radium in proportion to the amount of material we've used that even now we couldn't see it? What if that stain, even if it were the merest breath...
Go on.
Pierre, could it be that stain is radium? It's there! A radium! It's there! It's there! Pierre! It's there! It's there! It's there! It's there!
Okay, so that was, of course, radioactive radium. They named it that, and so they did discover a new element. She went on to win a award for in physics, so a Nobel Prize award for physics and chemistry. So she was quite accomplished. Sadly, Monsieur Curie, so Pierre Curie, was killed in an accident. He was run over by a horse-drawn carriage or something. So awful. All right, so remember, this is the end of Module 13, and you're going to take your test, and then hopefully I'll get a new quiz to you, and we'll be able to take that, okay? So, but now we're going to do a little lab time here. Since we can't do anything with active elements, you can understand why, I will tell you that Marie Curie did, in fact, die of leukemia. She did have cancer. And many people believe all that exposure to that radioactivity did damage her cells. But I also will tell you she was in her 90s when that happened. So earlier in that one clip, when she said her fingers healed, she had burns on her hands from touching that radioactive material. And from then on, she started to wear gloves. And so the radioactivity is very, very dangerous, and that's why we don't do it in lab, okay? But what we can do is something to try to replicate what's going on, and that is what I mentioned earlier, something called the quantum leap. All right, so we're not working with the nucleus. Radioactivity is to deal with the nucleus, but we can do chemistry with the electrons, okay, which is what we're going to do here. So what I have for you today is a little lab where we take these chemicals and we put them together. So we have something called luminol and then perborate mixture. We mix those together and add a little bit of copper. They're like little cubes or little crystals of copper to help the reaction to go a little more quickly. So I took a little scoop of each one of those and put them into that little vial right here with the lid. And then I have a beaker here. I'm going to add a little water into it. Now, what happened was I filmed this. I videotaped myself pouring this in there and then turning the light out. Well, the light, let me show it to you here. Okay, so there's the glowing. I'm going to confess to you right now that I'm holding a flashlight underneath this vial right here. So sorry, not to be cheating or anything. The idea is, though, the glow was so dim that when I turned the lights off, my camera could not capture it. My camera just didn't have enough, strength. It's my phone camera to capture it. And so I thought, well, I could just throw it out and not use it. If we had been in the class, y'all would have taken your little vials and shaken them, and you would have seen a nice little glow. All right, and so I'll tell you in a minute how that's happening. It has to do with chemistry, not physics, but at least we're looking at something glowing right there. For dramatic effect, I did put a flashlight underneath the bottom of that vial right there. So, but I have another thing to show you that's similar that's taking place, and that's using glow sticks. All right, so we've all used glow sticks before. You have two chemicals inside that plastic tube, and one of the chemicals is actually inside a glass tube inside the plastic tube, right? So then when I crack them, I break that glass tube, those two chemicals mix together, and then I produce this light. Okay, so like I said, it's chemistry going on, but let's pretend like it's a little bit of gamma decay, okay? So we have a gamma photon releasing off of there. But what I'll explain to you at the end what is really happening. Okay, here's a little video. What I did was, and I don't recommend you doing this, students, but I did cut the tops off of them and pour them together. We'll do a little color mixture right here. And this did, because the glow sticks are pretty bright, I was able to catch this in with my camera. So I'm going to mix these colors together and see if we can get some color mixture. Some people break these open and try to put them on their skin and stuff. Keep in mind, there's glass inside there, broken glass, okay? So it can be very dangerous. All right. See what happens when we pour the two of them together. Ready? Here we go. There's that glass in there. Well, I was hoping for a little more color change. See, it mostly looks yellow. See, my blue must not have been very strong. Yeah, so, all right. Still fun, huh? Okay, so I wasn't done. I thought, well, I can't finish there. That's, I'm just, it's a bummer to watch it that way, right? So what I did was I took another strong color, so a reddish color right over here. I broke that one open, and now I'm going to pour that into the beaker and see if it makes a difference. Okay, so let's see what happens. Boy, that yellow just overpowers everything. Oh, there's some orange. Here's orange. Okay, there we go. Okay, so you see it kind of worked there. There I had an orange color produced, and it's not as obvious in this picture right here, but it was very pretty, kind of a longhorn orange actually, when I mixed those three colors together. All right, so we're seeing. So what is happening here is that when I put those two chemicals together, it causes a reaction that takes place. And so let's say we have an electron here in the N1 orbital, right here. And it jumps up because it gets excited by the reaction happening with the other chemical. Okay, so the chemical reaction causes the electrons to get so excited they start to shake, and they actually jump up to the next level, to N2. All right, so when they jump up to level 2 here, they are not in their home orbital. They are in another orbital, and it took energy to put them up in there. That energy came from the chemical reaction. Well, over time, all the electrons are going to want to jump back down or fall back down to their home orbital. When they jump up to the next orbital, that's called the quantum leap. The quantum means a distance, right? Very, very, very itsy-bitsy tiny distance. They jump up to that, and then here you can see when it falls back down, this is known as the quantum fall, it falls back down to its home orbital. That energy that it took to push it up here gets released with a photon. Okay, so that's what you're seeing in glow sticks. That's what we saw in that little chemical reaction that we did with, that I did with the little chemicals there. And in class you would have done it. I thought we'd take ourselves into like that room where the nursery area where nobody's teaching and it was all dark. We could turn the lights off and you would have been able to see the glow really nicely there. So that's how that works. It's not exactly radiation, but it is an illustration of something that, it could kind of replicate it. But I didn't want to give y'all any poisons or give you any any radioactive, damage to your cells. Okay, so just kind of fun. And remember that you're going to now finish up Module 13, and then we'll start 14 next week. Okay, gang, I hope you enjoyed it. See you soon, I hope.